Do you know how to use pointers? You might say, I can write int pointer p. I know pointer p is dereferencing. I can get the value. I can even do pointer arithmetic like p++ or p+1. Doesn't that mean I know how to use pointers? But I can tell you bluntly, you probably only know how to write pointers. You haven't truly understood them. What you've memorized is just syntax, like reciting a formula without knowing the derivation. Many people's understanding of pointers stops at one sentence. A pointer is just an address. This statement isn't completely wrong, but it is very incomplete. A pointer is not a mere address. It's a combination of three core elements: address plus type plus a set of rules. None of these can be missing. Take the most basic example. When you write int pointer p, in your code, do you think you're just declaring here's a variable p that stores an address? Actually, this line sends three instructions to the compiler. First, the pointer variable p stores a memory address. Second, the memory space that this address points to stores data of type int. Third, every time you access this memory through pointer p, you should read 4 bytes. Under different systems and compilers, the size of int may vary. For example, in some embedded systems, int is 2 bytes, but the core logic remains the same. The type determines the access size. At the same time, the compiler will optimize the code according to the rules of the int type, such as catching, instruction, reordering, etc., essentially adapting to the CPU's access characteristics. So a pointer is like a navigation system. It not only tells you where in memory to find the data, but also how to interpret and operate on that data once you find it. This is the complete meaning of a pointer. It's not a cold numeric address, but a combination of location plus operation. Now look at a piece of code that many people have written. When many people see p equals p+1, their first reaction is address plus 1. For example, 200 becomes 201, but that's completely wrong. The real logic is address plus size of what the pointer points to. In other words, the step size of a pointer, the number of bytes moved by each +1, is not fixed at 1 byte. It's determined by its type. This is one of the most core characteristics of pointers. On Windows and Linux systems, for an int pointer, p+1 means adds 4 bytes to the address. For a char pointer, p+1 means adds 1 byte. The root of the difference is the memory size of the corresponding type. So the first core role of a pointer's type is to determine the pointer's step size. This also shows that a pointer is absolutely not a simple number. Its type directly determines its behavior. Ignoring the type means ignoring half the essence of pointers, and you will inevitably run into problems when writing code. Let's look at another classic misconception. Many people, when learning pointers, encounter code like this. You've probably written it, and teachers often say the array name is a pointer. Even many tutorials say the same thing, but this is really wrong. An array is not a pointer. Take this code, int pointer p equals array. The fact that it compiles and assigns successfully does not mean r is a pointer. This is the core misunderstanding. The real logic is, in most cases, arrays undergo decay. Simply put, the array name is automatically converted to a pointer to its first element. But remember, decay does not mean equivalent. They are fundamentally different. Like an apple and the shadow of an apple, they look alike but are not the same thing. The simplest and most direct proof is using the size of operator. Why are the results different? Because array is a whole contiguous block of memory. It is the data entity. Size of array calculates the total size of the array. 10 ints, 4 bytes each. The result is 40 bytes. P, on the other hand, is just a variable that stores an address. It is a reference. Size of P calculates the size of the pointer itself. On a 64-bit system, no matter what type the pointer points to, its size is 8 bytes, unrelated to what it points to. This distinction is crucial. Once you confuse arrays and pointers, many bugs become impossible to understand or debug. The earlier parts, with enough coding and debugging, you can gradually understand. Now comes the part that many people have never truly understood. Aliasing, the aliasing problem. What is aliasing? Simply put, if two pointers point to the same block of memory, those two pointers are aliases of each other. They give two different names to the same memory address. For example, code like this, two pointers of the same type pointing to the same memory, is not a big problem. The compiler can recognize it and no weird bugs occur. The real danger is aliasing between pointers of different types, that is, violating the strict aliasing rule. Consider this code. Can you see any problem with it? Syntactically, there is no error. The compiler won't report an error. It compiles and runs normally. But from the perspective of compiler optimization and program execution, this is very dangerous behavior. It's like planting a time bomb in your code. Because the compiler has a default assumption, pointers of different types will not point to the same memory. This is the core of the strict aliasing rule, and it's the foundation for compiler optimizations. This rule is not designed to make our lives difficult, but to allow the compiler to optimize boldly and improve performance. For example, when the compiler sees int pointer A and float pointer B, it assumes they point to different memory. So when optimizing, It can optimize operations on A and B independently without worrying about interactions, making the code run faster. But if you violate this rule and let pointers of different types point to the same memory block, the program may exhibit all kinds of strange behavior, such as optimization failure, making the code run extremely slowly, performance degradation, with the program consuming a large amount of memory, even incorrect runtime results where the code logic is correct but outputs garbled characters. So how to avoid violating the strict aliasing rule? 2 principles. First, avoid having pointers of different types point to the same memory whenever possible. Second, if you must do it for low-level memory operations, protocol parsing, etc., use char pointer or unsigned char pointer, because the C++ standard explicitly states that pointers of type char pointer can alias with any type without violating the strict aliasing rule. The compiler handles it correctly. Now let's tie everything together. You'll find that the type of a pointer affects not only syntax, but also low-level program behavior, including compiler optimizations, memory access patterns, and even CPU execution efficiency. This is the essence of pointers. First, compiler optimizations. If the compiler isn't sure whether 2 pointers might point to the same memory, for example, aliasing is possible, it won't dare to perform aggressive optimizations. It has to play it safe, no instruction reordering, no data caching, which directly degrades performance. If we can guarantee that pointer types are correct and the strict aliasing rule is not violated, the compiler can optimize freely and make the code run faster. Next, memory access patterns. Pointers of different types access memory in different sizes. Int pointer reads 4 bytes at a time. Char pointer reads 1 byte. Double pointer reads 8 bytes. At the same time, alignment requirements differ by type. For example, int typically requires 4-byte alignment. The address the pointer points to must be a multiple of 4. If the address is misaligned, the CPU may need an extra cycle to read memory, reducing efficiency. This is why pointer type affects CPU efficiency at a fundamental level. Another often overlooked point is cache behavior. The access pattern of a pointer directly affects CPU cache hit rates. For example, using an int pointer to access array elements sequentially, the CPU loads contiguous memory into the cache. Subsequent accesses come from the cache, high hit rate, very fast. But if you use pointers to access memory randomly, the cache will frequently miss, forcing the CPU to read from main memory often, which is much slower. The performance gap can be several times. This is why even when both use pointers, some people's code runs fast while others run slow. So in summary, a pointer not only determines where to access, but also how the CPU accesses. Only when you understand this can you say you've truly begun to grasp pointers and understand the low-level logic of C++. Now back to the original question, do you know how to use pointers? Maybe you can write them? But if you don't know what the type is doing, what the compiler is assuming, what the CPU is executing, then your code is only correct in appearance. If you truly want to understand C++, to grasp the low-level logic of how computers work, and to write efficient, bug-free code, escaping the trap of just copying code, welcome to subscribe to my channel. See you next time!